So I'm really pleased that we snagged Dr. Sapna Sharma from York University to come and speak with us today and join us. She's a professor in the Department of Biology at York and York Research Chair in Global Change Biology. She's also the inaugural director of the United Nations Institute for Treatment and Research, the Global Water Academy. Her research has led to her induction into the Royal Society of Canada College of New Scholars, and she's been named one of Canada's top 10 women water scientists. And I'll just say, so for my personal, so working group on the National Climate Assessment, especially the Midwest chapter, and looking at changes to inland lakes and coming across her dozens and dozens of research projects related to that. But what was really interesting is sort of seeing the bridge between the physical sciences and the social sciences and the impacts of loss of lake ice on communities and people and culture. And so really seeing someone bridging that divide has been very interesting. So welcome. Thank you for joining us. So let's give her a warm welcome, please.
Thank you for that introduction and the invitation to come speak here with you today. So I'm going to talk about lake ice today and the many different impacts. And before I begin, I wanted to make sure I introduced collaborators, students, and funding organizations just to thank them for the work that I'm going to present today. And I'd really like to take some time to thank John Magnuson, who's my mentor at the University of Wisconsin-Madison, who introduced me to lake ice like 15 years ago when I used to work on fish and climate change. And he's like, why don't you think about technology and lake ice? So it's been a great journey working with him as well as my many students at York University and international collaborators. And none of this research would be possible without funding. So I'm going to present the key messages I'd like you to take away right from the outset today. So you're going to hear a lot about lake ice, and throughout the talk, I'll present different scenarios of lake ice loss, depending upon different degrees of climate warming. And really, for me, what stands out is the importance of mitigating greenhouse gas emissions to preserve ice cover and also reduce the ecological and socioeconomic impacts that I'll talk about. Underlying that message is the importance of historical records. So I'm going to start by presenting like a historical overview of lake ice and lake ice research and the importance of open access data to really make global science possible and team science possible. And that's the third point as well. Is collaborating with diverse international teams across disciplines really increases our ability to do science, but also outreach and increase our impact of our work. So those are like the three underlying messages of today's talk. But I'm going to start talking about ice and a historical overview of ice. And I work with many different things, but ice is my favorite topic to work on. And there's several reasons why. So for earlier communities, ice has been really important for centuries for many different activities. So many years ago, ice was used from lakes and rivers for refrigeration purposes. We learned that about 100 years ago, ice from Lake Mendota in Wisconsin was transported in trains and railways all across the U.S. To help everybody keep their food cold. Ice festivals are a really big component of winters as well, and millions of people attend ice festivals every year. The biggest ice festival actually happens in China. That brings in the most number of people and economic dollars. I'm from Brantford, Ontario, which is the home of Wayne Gretzky. And so ice skating is a big part of how I grew up and many other Canadians grew up. And I'm going to talk about ice roads as well. They're really important to connect communities in the winter across the Arctic, but even in the Apostle Islands. in Lake Superior. And because ice has been used for so many centuries by a variety of communities, lake ice data has been collected for centuries as well, long before the advent of meteorological stations. The longest ice record on paper that we have, but it's a bit sporadic, is from Lake Constance in Germany. And this ice record goes back to 875 AD. And there was a nice tradition where a church in Germany would cross the frozen Lake Constance with the bust of John the Evangelist to a church in Switzerland as a sign of friendship between the two countries. But the lake hasn't frozen since 1963. My favorite lake, and I'll talk about this a lot more, is Lake Sua. And Shinto priests have recorded the date of ice formation since for millennia. And it's been on paper where we can track it down to 1397. So that gives us a really long history of ice records. Our best ice records are from gambling pools, because so many people are interested in observing ice conditions. So we have like a pretty good idea of when the ice on dates and ice off dates were. And we have thousands of lakes collected by community scientists from around the world that have been capturing ice on and ice off conditions for decades and centuries. And because I'm in the Midwest, I wanted to introduce community lake ice collaboration that I recently inherited about 5 years ago. So Ken Stewart from the University of Buffalo started this collaboration in the 1980s. And essentially, he just got the yellow pages from different states and started calling people who live near lakes and asked if they had ice or if they'd be interested in submitting some ice on and ice off for him. And with that process, he got 600 volunteers, and they've been recording ice on and ice off dates for about 1,000 lakes across the United States since 1989. And so when Ken used to do this work, he used to send letters with postcards. And there were self-addressed stamped postcards, and the data providers would, provide the ice on dates, ice off dates, and some information about ice conditions. And so I've been leading this project since 2019, and we started with this postcard route, but some of the people are now online. And so we also added a simpler website. We've developed this website, lakeicefreeze.com, where collaborators can submit their data online. For those who aren't online yet, we still send a few hundred letters each winter, and we sort of have this pen pal system, and as well as email. So to kind of reduce the gap and kind of make it more personal, I correspond with a lot of these individuals by email, and we get so much amazing information. So last winter, something I'm becoming interested in is freeze thaw events for ice within a winter. And there's very, very little data out there on freeze thaw events. And so I reached out to this community and asked, well, if your lake has any freeze thaw events, just send me an email and let me know. And so here's one of our community scientists, and he actually sent me an email each day that his lake would freeze, and then when it would thaw, and some information. But it was great because now we have a really comprehensive record for throughout the ice season, and we have this for several hundred lakes. So I think it's just like the power of community science really is in play when you think about lake ice, not only in the US, but around the world. And because lake ice data has been collected for centuries, the field of lake ice research has been quite extensive as well, and there's this rich history behind it. So typically, I only read papers in English, and so usually the furthest back we can get to lake ice research published in English is about the 1960s. And there's been great work done for decades. But recently I hired a postdoc from Siberia. He spoke Russian, he read German, and so he went through the Russian literature. And then we worked with some collaborators in Japan to go through the Japanese literature, and we uncovered this amazing, rich history of science in different languages, really highlighting some of the things that we still think about, like what are the climate drivers of ice? What are the roles? In 1891, they were already studying the roles of climate oscillations on ice. Some of the earliest studies on climate change were in Japan in 1921. Big data was being collected by the Russians, 20,000 records compiled across the Russian Empire in 1886. So one, it gave me a sort of, made me think, well, maybe I'm not that original. All of this stuff is already done. But two, it's just amazing to see all of the great work that has happened across international communities and different languages on something that's really important to many northern communities. So I'm going to shift from the historical overview slowly to start talking a little bit about the science. And I'm going to start with a story from Lake Suwa. So Lake Suwa is a lake in Japan in the Japanese Alps. And there's a Shinto shrine on the edge of the lake. And Shinto priests have lived here for millennia, and the lake is really important to their religion. And their tradition is that there was a god and goddess that lived together on the shores of Lake Suwa. And sometimes what happens when people live together for too long, they got into a disagreement, and the goddess moved out, and she built herself a shrine on the other side of the lake. And so we worked with Japanese historians and Japanese linguists to identify that what happened when the lake froze every winter was the Amawatari appeared, which is this sinusoidal ridge on the ice. And it was left by the God's footsteps, crossing the frozen Lake Suwa with his dragon to seek forgiveness from the goddess. And so every winter for millennia, Shinto priests have recorded the dates that the lake froze, the date that the Amawatari appeared, the shape, the direction, and celebrated the event with important leaders in the community. And so this tradition has been passed on through generations of the family. And even today, if the lake doesn't freeze, the Shinto priest will go every day until February 5th to identify has the lake frozen or not. And so John Magnuson went to Suwa, met Tadashi Arai, a Japanese limnologist, and worked with the current chief priest, Mr. Miyazaka, and they translated records from rice paper and historical artifacts into spreadsheets, into things that I could use. And the pretty cool thing actually right now is that we send our papers to Mr. Miyazaka and they're translated. And he's actually started recording. He started using this Excel. So we had a Zoom meeting a couple months ago, and he was like so proud to show us his Excel graphs. And he like recorded daily air temperatures and the ice on dates. And he's like, look at this great correlation. And so we're like bridging disciplines in a very different way. But from these spreadsheets, we can do some basic statistics and more advanced statistics. So we'll start with the basics. So here's our time series from the 1400s to the current and the future. In the first 250 years of the record, the lake did not freeze 3 times. And those 3 times actually corresponded to widespread famine in the region. In the next 250 years, you can see that there's been an increase in the number of ice-free years. And the Industrial Revolution in Japan began in the early 1800s, where there was widespread deforestation in the region, more people coming in, and just more development. And you can see that since 1950, the lake does not freeze 1 out of every 5 years. Since 1990, the lake is not freezing 8 out of every 10 years. So you see a very dramatic change. And we modeled Lake Suo under every climate change scenario that was available for every year until 2100. And there wasn't a single climate change scenario that predicted that Lake Suo would freeze again after the 2040s. So we have this long-standing, millennia-long tradition that stands to be lost in the coming decades. And so what are the drivers? I kind of give you a clue with what Mr. Miyazaki is measuring. It's air temperature. Winter air temperatures are the most important drivers of whether a lake will freeze or not. So here we've got winter air temperatures on the x-axis, percent ice-free lakes on the y-axis, and as you approach 0 degrees Celsius, which happens to be the freezing point of water, fresh water, you see lakes are more likely to have ice-free temperatures in those conditions. And Lake Suo is not the only lake that is experiencing ice-free years. Here we worked with the New York Times to represent some of our data and data analysis. And what you can see in orange are lakes that no longer freeze reliably every winter under current conditions. Under future conditions, we use the IPCC scenarios here. What you can see is this northward expansion of ice-free lakes. And this doesn't mean that this lake will never freeze again in this condition. It's just, it will have an ice-free year. And you can see that many lakes are going to likely experience this situation. We took it to the most extreme scenario here, which is permanent ice loss. And what you can see is under current greenhouse gas emission scenarios, about 5,700 lakes are permanently expected to lose ice cover within the century. And these are lakes across the United States, as well as in coastal regions and Europe. However, even mitigating greenhouse gas emissions quite moderately, we see a very different scenario with only 400 lakes expected to experience permanent ice cover. So what are the characteristics of these lakes that are most vulnerable? So first, there are lakes found in southern and coastal regions where winter air temperatures are above or hovering around 0 degrees Celsius. And then in the other case are the deep lakes are more likely to permanently lose ice cover. So Lake Michigan and Lake Superior have already began to experience intermittent ice cover where the bays are not freezing regularly every winter. And if we continue emitting greenhouse gas emissions at current rates, both Lake Superior and Michigan are expected to lose ice cover permanently by 2060, and under moderate conditions, 2080. However, if we do mitigate greenhouse gas emission scenarios, those bays and parts of the lakes will continue to freeze. So it's really governed by our decisions and our adaptations to dealing with greenhouse gas emissions. And I used to think, this is just a side note, but I've been doing climate change modeling since my PhD. And I used to think, well, I'm going to use these extreme scenarios just to get an idea of uncertainty and the ranges. And the extreme scenarios that I predicted in the early 2000s and late 2010s, early 2010s, have already come true in the 2020s in our extreme years. So now I'm less worried about using the gauntlet of scenarios because climate change is accelerating much faster than even our worst models predicted 10 or 15 years ago. And so there are still millions of lakes that still freeze. And as I mentioned, we have long-term records going back to the 1850s for quite a few of them. And this was a study that was done, the original study was done, published in Science in 2000 by John Magnuson, and we updated ice records from 1995 to 2019, 25 years of extra data. And you can see this very drastic change in ice on dates, in trends just here. But what we found was overall, ice duration is shorter by about 18 days per century there's some variation. So, for example, Bayfield Bay and Lake Superior has lost 60 days of ice cover since 1857. So there is variation. And the second important thing to note is that the rates of warming are 6 times faster in the past 25 years. And so when we had to recalculate the trend like 3 times because there were 108 days per century for the last 25-year period. And so ice loss is accelerating. Why? Lots of studies have documented why ice is melting earlier and freezing later. The predominant factor is climate change. So increases in air temperature related to increases in greenhouse gas emissions are contributing to less ice cover. Local weather also plays a role. Temperature, precipitation, whether it falls as rain or snowfall, snow cover, wind events, those all dictate when a lake will freeze or thaw, as well as these large-scale climate drivers. So solar sunspots, there's a regular 11-year solar sunspot cycle that influences ice conditions. And NAO events also influence the timing of ice on and off. And so I do a lot of statistics, but I try not to present too many of them in general talks, but I'm going to present one because I think it's cool. So this is the Torn River, which has a data set that goes back to 1693. This is Lake Suwa. The gray bars here are the breakpoints when the Industrial Revolution started in these 2 regions. And basically, I want you to look at the red blobs in black circles. And so what you can see for both of these is that before the Industrial Revolution, there were cycles, significant cycles in these ice records that extended from short to very long-term periods, 32 to 64 to even 128 years. After the Industrial Revolution, the long-term cycles seem to have disappeared. And this actually corresponds really well to climate data. And so when you think of the North Atlantic Oscillation, if you open up the textbook, it'll tell you it's a multi-decadal oscillation, 20 to 50 years long. But since the late 1970s, the 6 to 10-year period is much more influential. Same with ENSO. So back when the Shinto Creek started writing down their ice dates, ENSO was 50 to 60 years long, the El Nino Southern Oscillation Index. Now it's at about a 2 to 8 year cycle. And what that means is that, one, we're fundamentally changing how these large-scale climate oscillations are operating. But 2, those also correspond to more extreme events, which we're seeing in our temperature and our precipitation patterns, and then all through how it affects our lakes. So but it's something that we can observe and quantify in our ice days because they extend before the start of the Industrial Revolution. The other thing, so I've talked a lot about ice on and ice off, and whether a lake freezes or not. We're also thinking about ice thickness and ice quality. And I'm going to talk about this more at the end. But essentially, we did this global study called Ice Blitz. We all went out and in, I think, 6 or 8 countries, something like that, where we looked at ice thickness and we looked at the percentage of black ice thickness versus white ice thickness. And the white ice is the weaker of the 2. And what we found is that through the season, we're having increasing white ice conditions. And also, lakes in Ontario, in Canada, in Sweden, they have 100% white ice conditions in February, which is when people are most likely to be using the ice. And in Sweden, in this winter, 10 people drowned in February when the ice was thick enough to be skated upon, but it was all composed of the weaker white ice conditions. And so we're thinking about ice quality a lot more because it really pertains to human safety. So I'm going to talk about switch to some impacts. So we know that lake ice is changing. We know that we're losing lake ice, but what are the implications? There's actually quite a few. So we'll start with ecological. So we'll start with global lake temperature collaboration, 12 minutes. I will speed up. Okay, so here we collected water temperature from over 350 lakes around the world. In yellow, you can see the lakes collected by people, many close to universities or established collaborations. And in red, here we teamed up with NASA to provide satellite coverage. Back then, 10 years ago, that wasn't really so common, but nowadays it really is. And again, we made this data available open access. Now, what we found was that 90% of the world's lakes are warming. And interestingly, ice-covered lakes are warming twice as fast. And so it's the loss of ice cover is increasing the open water period and the amount of time a lake has to warm up. So why are lakes warming? We did a whole bunch of statistical analysis and we found two major drivers. First being climate change. Increases in air temperature are directly related to increases in water temperature. And the second being solar brightening and dimming. So the northern hemisphere is becoming brighter, which means that there's more solar radiation reaching the lake surface. So the lakes in the northern hemisphere are actually warming faster than what you would expect by climate change alone. Whereas the southern hemisphere is experiencing more development right now, releasing more substances into the environment. And so those lakes' responses were a bit more muted. This is not to say that we should release toxic substances into our atmosphere. But as I mentioned, here, this is a summary of thousands of papers in what we call this burning embers diagram. And basically, as temperatures increase, what we see is ice cover loss, surface warming, higher evaporation rates as well. And winter ice is really important in mediating water levels. So you can think of ice as a lid on a pot. And if you lift it early, you're going to have increased evaporation rates in the winter that directly can affect water levels. We've seen lots of amazing studies thinking about changing oxygen concentrations and also deteriorating water quality conditions as the shorter ice cover period increases the open water season, increases primary production and the likelihood of algal blooms, as well as habitat for native fishes. It's quite prominent. Okay, so now I'm going to move into cultural and public health implications. And the reason I started doing this is because I've been doing a lot of outreach on lake ice with the public. And many people say, well, why should I care? And I thought, well, if we can relate it to people, maybe they'll care. So that was why I started this foray of research. So first, we looked at skating. So we looked at cultural activities that are impacted because of ice and climate change. And we found here's this amazing skating race. It actually started in the Netherlands in the 1700s. But as ice has been lost throughout Europe, it keeps moving further north. And now it's in Sweden in Lake Malaren. And we looked at how long was the race, or was it canceled? And what you can see here is when air temperatures are warmer, the race is more likely to be canceled. I'm just going to go quicker. Yeah. Okay, same for, here's the Midwest example. We've looked at ice fishing tournaments in Minnesota. And we found that a single ice fishing tournament can bring in almost $1 million of revenue for a small town. So it's really important culturally, but also economically. And what you can see again here, we've got winter air temperatures and the percentage of canceled tournaments. And as temperatures go up, the percent cancellation of tournaments go up as well. And so recently we've tried to still trying to get people to care, we're like, okay, maybe we have to add a dollar value to it. And we've tried looking at economies and how much money could be lost. by losing lake ice conditions. And here we've just presented some values, some economic values in US dollars of some activities. And what we found in our study was that there's, 16 to $20 billion of local economies could be impacted because of loss of ice. This, I think, 5 minutes. Okay, this, I think, is the study that had the most impact on me. So we were wondering, so I'm in Canada, we're seeing more drownings. You hear about them in the news. My collaborator in Sweden was talking about drownings in their lakes from skating. And so we thought, are there actually more people dying because of unsafe ice conditions? And so what we did was we contacted police stations, coroners' offices, life-saving societies across the world to try to get information on how many people have fallen through the ice. There's actually like a death code for falling through the ice. The first step was actually finding out what the death code was. So the poor data scientists in my lab had nightmares for months of all the different ways you could die until we figured out what the death code was. And what we found was a really strong relationship between winter air temperatures and number of drownings. This relationship explains 50% of the variation. You'd think this is such a personal tragedy. How can winter air temperatures explain 50% of the variation? But what we found is as air temperatures approach 0 degrees Celsius, once again, more people are drowning through the ice. And this is lake ice, sea ice, river ice, creeks. And countries that have strong laws and regulations on whether or not you can go on the ice, those regions experience far fewer drownings. And in regions, this is northern Canada, the territories in Canada, which are comprised of many Indigenous communities who rely on ice for travel, for fishing, for hunting. They had by far the highest drownings per capita, sadly. The other thing that caused a lot of nightmares was identifying who was drowning. And the predominant drowners are kids. Kids under 9 are the most likely to drown, just playing on the ice, not knowing what ice conditions are, as well as young men from the ages of 15 to 24 who might be snowmobiling or just trying to have some fun on the ice. So this really impacted where I want to go with my research now. And on ice. So first is thinking about ice quality and how will ice quality and ice safety change with warming temperature. So you've probably been in the Midwest, you've probably all seen this amazing figure about how much ice thickness is required for safe use. And this assumes black ice conditions. But what we're learning now is that black ice conditions are becoming pretty rare. And what does this mean for communities? And so this is some graphs summarizing 14 billion data points. And basically what I want you to check out is the percent loss of safe ice just being on the ice with 3 degrees Celsius warming. And I think, so most of this in the United States and North America. So even if the lakes freeze, they may not be safe to use. And this is assuming black ice conditions. And what we're finding is that there's increasing white ice conditions, and that contributes to even less safe ice. So we're suggesting at first just doubling the amount of ice that's on a lake or a river before you go use it. And we've modeled how much less weight these lakes can sustain. Here's a cartoon of 14 billion units of transportation infrastructure. So we're trying to take it outside of ecology and thinking about ice roads and how those might change with climate change. And we're now expanding into beyond the cryosphere. So sea ice, snow, permafrost, river ice, what that means for transportation infrastructure, such as ice roads and snowmobile trails, but also marine shipping. So marine shipping is increasing as sea ice is declining, but ice roads are declining. So what does that mean for coastal communities versus inland communities? Who can access food? That's we've put together a team thinking about food security. So can you access market food, but also country food? So changes in marine shipping, for example, is changing the distribution of narwhal. And so communities in Pond Inlet in very high Arctic in Canada, they rely on narwhal for traditional food, and the narwhal have moved. And so they're questioning, well, do I eat killer whales now? Which they don't want to be eating them. So what is my new food source? Also the reindeer and caribou across Scandinavia, and Canada and Alaska, those distributions are changing, but accessing safe snowmobile trails to get to caribou and reindeer habitat and territories is less safe, is increasingly less safe. So we're looking at what that might mean for health, ultimately, for physical health and mental health of these Arctic communities. And so this is the next 3 years is thinking about how ice is changing across the circumpolar Arctic, and what this means for transportation, for food security, for health, and also the legal implications. And we brought in a legal team to identify, can we advocate for Indigenous communities, with Indigenous communities, to advocate for safer ice conditions. And the ultimate goal is to try to create an ice safety dashboard, identifying when conditions are safe for use, and that's the goal for the next couple of years. And so thanks again for listening so early in the morning, and I'm happy to see you.
Amazing presentation, as I promised, right? Bridging sort of like the physical sciences with implications for people. And I imagine many of you, like me, have many feelings after seeing your presentation, both inspiration on sort of the innovation as well as a bit of sadness for the loss. So a couple questions. I guess just to comment on the sadness, I know that it's a little much when you see the models, but I also feel like we have to know, right, what's coming so that we can adapt and mitigate for those. And so I think for me, because the models can be kind of depressing, but I'm a very hopeful and positive person, so I try to counteract that by trying to do things that hopefully have impact for communities and people. So I think there's like ways you can go around it, and that's how I deal with like the depression of these models. Thank you for sharing. Yeah, Gabe.
I was saying, speaking loudly, I had a fantastic presentation. I was really curious about, you mentioned the Industrial Revolution and that with a kind of step change in characteristics of the winter ice, which I thought was fascinating. But with the Industrial Revolution also came flat darkening of ice, maybe from flat carbon. Does that play in on any of these analyses?
That's a great question. That's not something we tested in explicitly, because back then all of the information that we had from them was the timing of ISON and ISOP, and no model is perfect, and so that could be explaining some of that unexplained variation that we're not seeing. So that's a great comment that we haven't explicitly considered.
Yeah, thanks. Excellent presentation. As an ice fisher person, I experienced a lot of what you presented. Literally canceled ice fishing tournaments in the frozen prairies of North Dakota last year. I'm also curious about, you talked about relating this to the individual person. And what about vehicle loss? We had a lot of vehicles, UTVs, trucks, SUVs going through the ice last year, Minnesota, North Dakota, and I imagine in a lot of other places as well. Is there an opportunity to quantify that?
That's a good idea. So we've started with quantifying the ice roads, which require like 42 inches of ice for use, and then working with engineers to figure out like how do we engineer ice conditions so that they're thicker, but we haven't thought about the trails and the lake ice conditions for vehicles, smaller vehicles at this point. So that's what we're hoping to think about in the coming years, is not just thinking about the winter ice roads, but also, like you said, what that means for vehicle use on a lake, on a river, through permafrost. And we're starting with community relationships that we're building in the Arctic. And then I think we'll grow from there. So thanks for bringing that up and raising that as an information.